And finally, my favorite topic, which is authentication and authorization. And this is probably one of those areas which we encounter every day. I'm pretty sure all of us have used authentication screens before. We have logged into different platforms. You have signed up into different platforms. Those are basically called the authentication flows. And to summarize everything in two sentences, authentication can be explained as a mechanism to assign an identity to a subject, to say in the technical terms, and basically to answer the question of who are you. Authentication basically means who are you in a given context. In a given context, the context can be a platform, operating system, or your phone, anything. The answer to this question, the process of finding the answer to this question is called authentication. In the same way, the answer to this question, which is what can you do in that context, in that platform, in that operating system, all your capabilities, all your permissions, to say in the technical jargon, those things, the process of finding the answer of the question, what can you do in a particular context, that process is called authorization. Those are the two sentence summaries of the whole topic. And this is what we are going to talk about in this video. And we'll dive into different aspects, different components of authentication and authorization. Basically have a general high level and a technical understanding of how it works, what is the importance, what are the different things that make up and build the whole authentication and authorization flows and everything surrounding it. Now, before we dive in, let's have some historical context of authentication. So first we're going to start with authentication, right? And for authentication, let's have some historical context of what was the use of it, how did we reach here, and how did we reach to the modern methods of authentication. So the story starts somewhere in pre-industrial societies. And here, authentication was pretty intrinsic. By that, I mean it was implied. So an identity of a person or a subject was the same as the subject's recognition. And what that means is someone who is already respected in the community, let's say a village elder, could vouch for a person, and whatever deals were made during those times were sealed with a handshake, an act of symbolizing mutual recognition and agreement. Even though it was pretty elementary, this method leveraged a form of authentication based on human contextual trust. It was based on humans, right? It was based on trust. And that's how people started the initial methods of authentication. But as populations grew, interactions extended beyond familiar circles, like beyond this society, beyond this village. Implicit trust mechanisms failed to scale. This cannot scale, right? Because this person whoever this is in the community, the village elder, that guy is not trusted in all the communities, in all over the society, in different countries or continents, right? This method cannot scale. So this marked the beginning of his search for explicit authentication. Explicit auth. Initially, we said this was implicit auth, which is based on trust. People needed proofs of identity that could function independently of personal acquaintance, independently of any person. And that led to seals and cryptographic era. So by the medieval period, society needed a system that scaled beyond personal recognition, which we talked about earlier, just based on people of trusted reputation who can vouch for other people or other subjects or other deals. So society needed a system which can scale beyond that. And during those times, people came up with this system which is called a seal. It was wax seal. People who have watched different movies or series of historical times, you must have come across this. This is like some seal, and this was attached to different letters or different agreements as some form of authentication or some form of agreement. And it was one form of early cryptographic mechanism. a seal which was of a unique pattern, and this is put on documents which acted as signatures. Today we have digital signatures and handwriting based signatures. This was one kind of signature during the medieval period, and these seals functioned as the first widely adopted authentication tokens. You can say these were one kind of authentication tokens during those times, and they were kind of a physical representations of identity that relied on possession, something you have. If you have this seal, you have this in your possession, then you are said to be authenticated and you can verify yourself using those seals. Seals had their vulnerabilities. They were prone to forgery, marking the first recorded instances of authentication bypass attacks. So we have in the modern times different types of authentication attacks. One of those kinds is a bypass attack. A bypass attack basically means skipping the authentication with malicious intents. Forging these kinds of seals for malicious intents was one kind of bypass attacks during the medieval period. And this led to the evolution of more sophisticated mechanisms, including things like watermarks and encrypted codes, right? Used in different trade documentation, setting a foundation for cryptographic thinking. People started thinking more about codes, how codes can evolve to prevent different kinds of attacks and forgeries and frauds. And that led to the next era, which was passphrases and shared secrets. So we can say during the times of industrial revolution, a lot of progress happened in terms of machines, right? In terms of machines, a lot of progress happened and the whole world started to change. And at the same time, communications systems also started to get upgrades. Communications systems also started to progress. They started to evolve into more secure and more advanced form of communications. And during those times is technology called telegraph was introduced. And telegraph became a critical infrastructure, and with it came the need for secure message validation. And operators, whoever was operating these telegraphs, they used pre-agreed passphrases. You can call it also password, but there's some form of passphrases. And that was an early form of shared secrets. And these passphrases were the same as static passwords, like they are not dynamic. They decided on one static string, one static password, and they used it as a passphrase among them. And that relied on the principle of, we can say, something you know. Earlier, the principle was something you possessed, which was a wax seal, some kind of token that you possessed that you can show to verify yourself. And that got evolved into something you know, which is much better in terms of security. And that was one step into the evolution of which in the modern times you know as password. That time it was called passphrases. And that the whole principle of authentication changed into something you know, which is inside your brain or in some form of communication, either written or verbal. And after that, we can skip all that to the modern times of computation, computational architecture, and all the modern authentication that we know of. And the first form of computation, which we already know, is mainframes. Somewhere in mid 20th century, and authentication entered its first digital phase. So there is a story called in 1961, researchers at MIT's Project Mac, they were working with something called compatible time sharing systems, also known as CTSS. And they introduced the concept of passwords for multi-user systems. Basically, they were trying to come up with some kind of system which will allow multiple users to use a computer without sharing the data, without sharing a user's data between each other. And what they did was they stored password in plain text, which was in itself a very critical vulnerability. And that came into view when one of them printed the password file in plain text, because it was a plain text file, you can print the password. And that was the time when that vulnerability came into place and people got aware of that. And this incident, the printing of the password file, this incident marked the genesis of secure password storage mechanisms. Right now, we have this philosophy that passwords should not be stored in plain text. And this incident of someone printing the password file in a printer, that was the initial idea that motivated people to the philosophy of storing passwords securely. And that led to different innovations like hashing that you use pretty frequently today to store passwords in our databases, and different cryptographic algorithms which transformed passwords into irreversible fixed length representations. So hashing is basically cryptographically, so you can say there is some kind of algorithm, it does some kind of computation, you provide it a plain text string, provide it, and in turn it returns you a hashed string. A hash string basically means it has a computational algorithm. It will transform that string, the plain text, into a fixed length. The length won't change. It does not matter you provide it a 3-character string or a 100-character string. The length of the hash will stay the same depending on the hashing algorithm, and it will provide you the same result for the same string every time. That was the promise of the hashing algorithm. So these kinds of algorithms started to emerge during this era. And authentication began to align with the principles of confidentiality, integrity, and availability, the core tenets of information security. And then in the 1970s, an explosion in cryptographic research driven by the work of great people like Whitfield Diffie and Martin Hellman, the people who have come up with cryptographic algorithms. Their invention of the Diffie-Hellman key exchange introduced the concept of asymmetric cryptography, enabling two parties to establish a shared secret over an untrusted medium. That was the first time asymmetric cryptographic technique. Asymmetric cryptography became the backbone of modern authentication protocols. All the protocols that we have now, those are all based on asymmetric key cryptography, and they are also called PKI, public key infrastructure systems. And this era also gave the rise to protocols like Kerberos, which introduced ticket-based authentication. And Kerberos relied on trusted third parties to issue tickets that verified both the user and service identity, which is a precursor to token-based authentication systems that we have now. And we will shortly look at those token-based authentication methods. Right now, we are just exploring how all the dots connect together, how the historical context led to what we have today, led to what we use today. All the different algorithms, mechanisms, methods, and standard practices. Moving on, if we go forward, during around 1990s, when the internet was growing, a need for scalable authentication methods was also rising. Simple username and password-based systems were not enough, and they were not strong enough against brute force and dictionary attacks that are newly coming during those times. And that led to something called that we have MFA, which is multi-factor authentication. So MFA came with the idea of a combination of different principles. It combined, let's say, 3 things. One thing is something you know with something you have with something you are. Basically, something you know can be passwords or pins. Something you have can be cards, smart cards or OTP generators. Right? And something you are, that is your personal identification. It can be biometric data like fingerprints or retina scans. Right? And MFA came with this revolution of combining different principles, different layers of principles that provide a combined security to all kinds of authentication applications. And because of that, biometric authentication emerged as a groundbreaking development, leveraging pattern recognition algorithms and statistical models to identify users based on unique physical traits. However, biometric systems introduce challenges of false positives, negatives, and template security. So that was also not enough. Biometric security was not the one-step solution for all the problems that were emerging during those times. And after that, you can say we are finally into the modern times. Modern times which we can call 21st century, the time that we live today. And in the 21st century, the rise of things like cloud computing and mobile devices and API-based architectures, they demanded advanced authentication frameworks. None of the above authentication methods or frameworks or principles were enough. So we needed more advanced, more technically robust implementations of authentication. And because of those demands, a lot of different authentication components or authentication techniques emerged. And among those, we can say some of the important things are Auth, OAuth 2. These are the ones that we still use today, and these are the most popular ones. I'm just talking about the different components of authentication that we are going to discuss soon. Another thing is JWTs. Then we have zero trust architecture. We also have for passwordless authentication. System like web authentication eliminate passwords entirely, relying on public key and private key stored in hardware devices. We'll discuss OAuth 2 and JWT shortly. And then this is the time that we live now, and this is what the future looks like as of now. During the time I record this video, we have a couple of candidates for the future of authentication world. We have decentralized identity that is created using popular technologies like blockchain. They offer a lot of features, robust features for authentication. They are still in early stages now, and people are still experimenting. They are promising and a potential candidate for future of authentication. Then the second is behavioral biometrics. We have this concept called post-quantum cryptography. So post-quantum cryptography is basically the idea that once quantum computers start getting used heavily, they are going to break all the cryptographic algorithms that we have now, that provide the sense of security that we have, that our data, our passwords, our sensitive data is secure. Because of these algorithms, we have RSA and different types of public key, private key algorithms that are very difficult to break with the hardware, with the computation capability of systems that we possess today. So once quantum computers get used heavily, once they get common enough, all these algorithms, cryptographic algorithms, they are going to break, because quantum computers are very, very, very fast in terms of what we have today. And these algorithms are not made for that. This concept called post-quantum cryptography is basically cryptographic techniques that are even secure for quantum computers. We already have some algorithms as of my knowledge, and you can read up on that. All in all, this is pretty much all the historical context that we have of authentication in our knowledge. With that, let's move on to the technical part, the interesting part that you as a backend engineer should have the knowledge of. Before I jump into authentication, I want to introduce 3 components that we are going to discuss again and again in this whole video. So I feel it's better to introduce them right now before you start anything, so that you have some kind of context or some kind of familiarity when you hear them. And these 3 are very important in all the authentication and authorization flows. They are sessions, JWTs, cookies. And we'll discuss what are they. Let's start with sessions. When the web started, when the whole internet game started, HTTP protocol that we use for our client server communication. If you have watched my HTTP video, then you'll understand what I'm talking about. HTTP emerged as the backbone of all the communications between client and servers. And by design, HTTP was stateless, which basically means HTTP treated every request as an isolated interaction. So it did not remember what was your previous request. Every request had enough and all the information that the server needed to perform the business logic. That's what it basically means for a stateless protocol. It has no memory of any past exchanges. And this was enough, and this was ideal even for the earlier web, the web that we started with, which mostly consisted of static pages, static images, and data that people mostly read about. Just you look at a website, you read something, and you move on. Readable data, static data that we can call. And people did not need continuity. People did not need memory between different requests. No, that was not a need when it was designed. However, when we evolved, as the web transitioned into dynamic content, and it happened very soon, and when it evolved into dynamic content, the statelessness of HTTP became a bottleneck. How? Because we had different types of websites, a highly interactive websites like e-commerce sites, which needed to remember what are the items in your cart. That is one example of the interaction. Or how could a user remain logged in while navigating between different pages? That was another need. And these questions marked the beginning of stateful interactions in the web. Stateful interaction. It was the need for stateful interactions. Otherwise, modern websites, modern needs of technology was not met. That's why we needed the web to be stateful, which HTTP was not. And that's why the concept of session came into play. A session basically provided a way to establish temporary server-side context for each user. And it has some kind of memory about the user that the server can have to remember the user when the user makes a request next time. So how did it work? First part was session creation. When a user logged in, the server created a unique session ID and it stored it alongside the relevant user data, whatever the user's role, name, whatever the data the server needed to do different kinds of operation again and again. It stored it with the session ID, whatever the cart items of the user is, all those information that the server needed repeatedly. It stored it in a persistent store. It can be a database or it can be a Redis store, which is a in-memory persistent store compared to database, which is a file-based persistent store. So the server stored the session ID with all the user data, the cart items, or whether the user is authenticated or not. All these different kinds of information with the session ID is stored in some kind of persistent store. And the second phase is the session ID. This key, unique key, was sent to the client, which is a browser. The server is somewhere in the remote. It is somewhere in the cloud. And the session ID is sent to the user, which is on a browser as a cookie. We will see what a cookie is, but it is sent to the user as a cookie. And all the requests that the client made after that, after the session being created, included that cookie with those requests so that the cookie can have the session ID, and using this session ID, server can fetch this information, all the cart items, users data from this persistent store. It can be Redis or database. So basically this session ID enabled the web to have some kind of memory, enabled the servers to have some kind of memory for the sake of the user, for the sake of the client. And in the third phase, you can say these sessions were short-lived, which means they had an expiry date. So let's say if the session's expiry date is 15 minutes. So after 15 minutes, the user sends this session ID to the server and they are expired. So the server creates another session and sends the session ID, stores the user data in the persistent store, and that's how it works again and again. That's how this whole session thing works. And initially sessions started with file-based sessions. Those were the early session implementations, and that stored data in files on the server. Even though they were simple, that approach suffered from scalability issues as the number of users grew. And servers started to implement database-backed sessions. To handle large user bases and to make the server scalable, sessions data moved to databases, which provided faster lookups and persistent storage across server restarts. That data is stored in the databases, and even though the server restarted, the session became available. The session stayed available to the server. And eventually we move to distributed architectures. And during this era, the session storage, the persistent store where the servers store the sessions and the user's information, move to distributed storage. Distributed storage like that we have Redis, which is a in-memory store. In-memory store basically means storing data in RAM compared to hard disk. That's a one-line explanation. Or memcached, which is also another in-memory store. And servers started to use these. These were comparatively faster as compared to DB lookups because they were in-memory stores. So that's how the storage evolution of sessions happened. And we still use sessions even today for the same purpose, to provide some kind of memory to our servers. Moving on, then we have is JWTs. And this is a very popular technology in the current times. These are very popular, and we will see why they became popular. What are the advantages that they offered as compared to our traditional session-based authentication approach? What are the additional benefits of using JWTs that cause their popularity? So, continuing our earlier session discussion, by the mid 2000s, web applications grown into globally distributed systems. And stateful systems, even though they were effective, they caused a bottleneck. Because first thing, memory. Maintaining session data for millions of users became costly. So right now we are talking about what led to the emergence of JWTs. So first thing is, retaining session data for thousands and millions and billions of users became a large overhead for a lot of servers. Second thing is replication. What this means is, in distributed architectures, synchronizing session data across servers or regions. One server could be in one part of the world, another server could be in the opposite part of the world. So synchronizing the user data across these servers from different regions introduced latency. So the authentication flow introduced latency, which is basically means delays in authenticating the user, and consistency challenges because of the synchronizing need. And that led to the birth of JWTs. JWT. Because developers sought a solution that could offload state from the server while maintaining security and integrity. That's how people came up with JWTs. So JWTs, which were formalized in the 2015, were a stateless mechanism. Stateless. This is the word to focus on. Stateless. There is stateless mechanism for transferring claims. We'll see what claims are shortly. Transferring claims in a stateless manner between different parties. Let's say two systems. Transferring claims in a stateless manner between two parties or two systems. And the key innovation here was self-contained. JWTs were self-contained tokens. JWT tokens contained user data, stuff like user ID, their role, and the cryptographic signatures in one token, which are base 64 encoded. If we go to the website called jwt.io, we can take a look at what a JWT looks like. Okay, so this is what a JWT looks like. This is the whole base 64 encoded JWT string, and JWT has three parts. To get a high level idea, we can look at the parts, which are, first part is the header. The header basically specifies metadata such as the signing algorithm, which can help the server to get some information on what was the signing algorithm that was used while the JWT was being created. So the first part, the header, basically contains metadata about the JWT itself. Stuff like the signing algorithm. And the second part, which is the payload data, the data of the user, the data that we store in the JWT, the data that we actually need. This also has some kind of format that we typically follow. So the first thing is sub. Sub is the field where we usually store the user's ID. We store the user ID, and the user ID can be in any context. It can be a user ID from your database. It can be a user ID from an auth provider. It can be any user ID from any context. This is just a storage mechanism, right? You store the user ID of the user in the subfield. In the IAT field, this stores when the JWT was issued. That is the information the IAT field stores, which basically means issued at. That's the full form of IAT. And then we have optional fields. You can store the name of the user and the role of the user, whether the user is an admin, as a member, or it is a role of editor or a viewer or a writer, whatever the role is. You can store information like that, different kinds of information in different kinds of fields inside the payload. Okay, this is the part where you can store information. And the last part is the signature of the JWT to verify that whether you are the one who issued it, whether this data has been tampered or not, right? And you can do that with a secret key that you can generate and keep for yourself. Only you have an access to it. If someone makes any change to the JWT and you verify that JWT with your secret key, then the validation will fail because someone made some changes to the JWT and it is not tamper proof anymore. And now you know that. So that is not a JWT, a valid JWT anymore. That's how you can verify users' data in a stateless manner. Now you don't have to store the session information anymore. Whole session verification mechanism just became stateless. It happens with every request. It is very lightweight and saves a lot of storage cost. So these are the advantages that JWT is offered that made a lot of things in the authentication workflows very simple. The first thing was statelessness, which basically enabled no server-side storage costs. Second thing was scalability. Scalability basically means a lot of servers these days use the microservice architecture and distributed architecture, and which means a cookie issued from one server cannot be used for a server which is in another domain in a microservice architecture. So using technology such as JWT enabled a client to send the JWT to different servers, and all the servers will have the secret key of the JWT, using which they can decode the JWT and verify the user's identity. So now a lot of servers, a server can be scaled to a lot of instances and they won't have to worry about user authentication anymore. All the servers can do the user authentication at the same time using a shared secret key. And that was one of the major benefits of JWTs, and the third thing is the portability. And because of the lightweight nature, because of the URL friendly nature, because of the base 64 encoding string format, JWTs could be passed between different systems. They could be stored in local storage, even though you should not do that. They could be stored in cookies and a lot of different limited space storage systems. They're very portable. You can send them in URL values and a lot of other advantages that JWTs offered in terms of portability. And on top of that, they also introduced some challenges. One challenge was token theft of token. Since JWT was stateless, there was no stored mechanism that the server used to validate the user's identity. If someone has access to your JWT, now they can impersonate as you. They can use your JWT to perform actions on behalf of you. That is the one disadvantage of JWTs. And there is no mechanism from the server side to invalidate that token until it expired manually, unless the server changed its secret. The secret using which the server verified all the users. Now, the problem with that is, if the server changes the secret to invalidate one token, now all the users of that platform, of that system, will have to log in again and get new JWTs just because the server wanted to invalidate token of one user. That was one thing. Second thing was revocation. So for some reason, if the server wanted to revoke some users' access or some users' access to the platform or access in different systems, the server could not do that because JWTs, since they are stateless, you have no way to track the status of a JWT token. Until they are expired, you cannot really do anything. So these are the two major disadvantages that came up because of JWTs, because of the use of JWTs. Even though these days we found some kind of solution for that. For example, for the first thing and the second thing together, we use a hybrid approach. of using JWTs. So using a hybrid approach again raises some questions. First, I'll tell you what a hybrid approach is, which we came up with to beat the above two advantages. So this is how it works. The user logs in and the server sends it a token, a JWT token, which the user stores in its system. Okay. And with every subsequent request to the server, the user sends a JWTs in either a authorization header or in any other form or a cookie or anything. Okay. And that's how the server gets the JWT. It verifies the JWT with its secret key and make sure the user has proper access, or it can identify the user. That's how it works in a JWT based workflow. So in a hybrid approach, what we do is we combine statelessness with statefulness. What that means is, in a JWT typical workflow, we don't make an additional lookup in our storage. The storage could be a database lookup or a in-memory lookup like Redis or Memcached. We don't do that. We verify the JWT with a secret key and we find out who the user is using the user ID that is stored inside the JWT. That's it. We don't do any additional storage lookup. Now, in the hybrid approach, what happens after you verify the JWTs, after you have the verification step passed, you maintain a blacklist of JWTs in your persistent storage. Again, it could be a database call or a in-memory call for Redis or Memcached. And using that, you can temporarily block some users, revoke access for some users in case of some users account being hacked or some user doing some malicious activity. You can temporarily block their access using a blacklist. Now, the question it raises is, the whole point of using JWT was their statelessness. And if you are doing a persistent storage lookup for checking the validity of the JWT, why not do the statefulness? Why not do the stateful approach in the first place, which can provide this advantage and it is considered more secure? So these are the kinds of questions that we frequently see in the industry. Typically, the advice is don't think about all these different authentication strategies and all. Go with an auth provider. We have a lot of different types of authentication providers. We have Auth0, we have the modern alternatives like Clerk and all. That's their headache. That's their headache to worry about what technologies, what components of authentication to use, which is more secure, which is a more secure way, which are more secure techniques and everything. Starting from the algorithm to hash to salt, all the different parts, all the different headaches of authentication, which creates a secure authentication system. That's their headache. It's very important if you are building a medium to a largely complex system. It's a good idea to go with an external auth provider. Even though it's a good idea if you're learning backend engineering to implement your own auth, understand how the different parts work and understand the trade-offs, understand the advantages and disadvantages, everything. After that, in a production system, go with the auth provider. Go with an auth provider unless you're very confident about your authentication workflows. Okay, that is my 2 cents about what you should do with all this confusion about what is right, what is not and all. And the third thing that we have is cookie. And we have already discussed and talked about using cookies in the earlier 2 examples. For example, in the session-based authentication, first I'll explain what a cookie is. Cookie is basically some way of storing a piece of information. It can be any string, any value. It is one way of storing this information in a user's browser from the server side. That is the important part. Using cookies, servers now can store some information in clients' browsers from this side. So this is a very nice feature offered by browsers. So using the HTTP request workflow, a server can store some kind of information in the user's browser, given certain conditions that cookie is only accessible to that server. A server cannot see other servers' cookies. So that is a nice feature. That is a nice security feature offered by the browsers. So using this whole mechanism, cookies and all, a cookie set by one server in a client's browser will be sent in all the subsequent requests to that server. So this whole workplay of cookies the server storing the cookie in the user's browser and the cookie being sent to the server with every subsequent request from the user's browser. This whole workflow enables that during the authentication workflow. Let's come here. During the authentication workflow, first a client authenticates with username and password to the server. And if the authentication is successful, the server sets a cookie. We can say a cookie with the authorization token. This looks something like a JWT token or a session ID. It can be whatever, depends on the implementation. It stores it in the client's cookies. And in the subsequent request, the client's browser, it can be Chrome, Firefox, Opera, whatever it is, sends this information, this cookie, to the server so that the server can validate authenticity of the token, and it can authorize, it can identify the user, and it can authorize the user and do all the workflows that comes after the authentication. So cookie is a very nice way to automate the process of server sending the token to the client, and the client sending the token back to the server with every subsequent request. All of this can be done from the server side using the mechanism called cookies, because the server has access to client's cookies that is stored in the browser from the server side. That is the part to focus on. And that was about 3 major components of modern authentication. Now let's move on to different types of authentication types. We pretty much already have discussed what are the 2 major types of authentication, but here we can keep that as a topic at hand and discuss them at a very high level. The first part is stateful authentication and the second is stateless. We have also other methods of authentication. We have API key based authentication. We also have Auth 2.0 based authentication. And these are pretty much all the major types of authentication that I can think of that we use as backend engineers in our day-to-day lives. Okay, let's dive into each of these types and see how they work and what are the advantages, disadvantages, and when should you use which one, and everything about them pretty much. Okay, let's get into stateful authentication. First one is a stateful. Okay, all in all, this is what stateful authentication typically looks like. Okay, we have client here. It is a browser. Let's say it is a browser. It's a Chrome. We have the client here, and we have the server here. Okay, first step, during authentication, the client sends username and password to the server. Username or password or email or password, whatever the authentication mechanism is, to the server. The server checks the validity and the correctness of the password and the username on the email and all. If they are correct, if the user is eligible to authenticate into the platform, the server generates a session ID. We have talked about sessions already and this workflow also already, but let's just discuss it again. A session ID and the user's data, whatever it is, and bundles them, user data, bundles them and stores in Redis. It can be a database also, but mostly platforms use Redis because of the fast read time, fast access time of the Redis as compared to our traditional databases. Okay, and it stores in the Redis and it sends the session ID back to the client, in a cookie. It stores it inside a cookie, a HTTP only cookie, which means JavaScript cannot access the cookie. JavaScript cannot access the value of this session ID. And the server sends the session ID to the client back in a cookie. And because of the nature of the cookie, because of the nature of the subsequent request attachment quality of the cookie, what happens is all the requests that happen after that one will have this cookie where the session ID is present. And the server will get this cookie. The server will take that session ID and it will check the existence of that session ID in Redis, the expiry of that and the user's data and everything. And it can identify the user, it can authorize the user or whatever it wants to do. And the user has the ability to call the API. That's how the typical stateful authentication workflow works. And the session ID can be any cryptographically random string. It can be a JWT token, whatever. It depends on the implementation. And that's all about stateful authentication. Moving on to stateless authentication. stateless. And this is how stateless authentication works. We have a client again, it's a browser, and we have a server. The user sends the username or password, the email and password in the first request. While the user is trying to log in, the server checks the authenticity of the username and password, and if they are correct, the server generates a signed JWT token with a secret key. The server has its own secret key using which it can sign JWTs and it can verify JWTs. This is very important. It has to be stored somewhere securely so that it can sign or verify JWTs. And the server creates a new JWT token which has the user's information, things like user ID, user role, etc. And it sends the JWT back to the client. Okay. Then in all the next requests, if the client wants to identify itself, it wants to authorize itself, what it can do is it can send the JWT back in a header. You can send in any way, but the standard is you can send in a header called authorization, and you paste the JWT here and you send it to the server. The server extracts this token and it tries to verify it using the secret key that it has, and it verifies it, and then it can find out the user's ID. And if the verification is successful, the authentication is successful, and the user can have a successful API response. Otherwise, the server will throw an error called unauthorized or forbidden or whatever the convention is. And that's how a stateless authentication works. Because it's called stateless, because in a stateful authentication, we need to look up a persistent store. It can be a database or it can be Redis. And in a stateless authentication, whatever information that we need about the user is stored in the token itself, in the JWT token itself, which is a signed token. And to verify the authenticity of the token, we have a secret key. So it's a self-sustainable, self-containing token which has the user's information. That's why it's called a stateless token or a stateless method of authentication. Now, when should you choose which one? So to answer that, you have to understand the pros and cons of both the different kinds of authentication mechanisms. In a stateful authentication system, the pros are first, you have centralized control. You have centralized control over all the sessions. You have real-time information of all the active sessions of your users, right? Because you have a persistent store to verify, to get that kind of information. And using that, you can easily revoke access of a user. You can revoke a session. You can log out a user because you have the session, you have the control in your hands. And it is well suited for applications with modern traffic and strict session requirements. And in my opinion, most applications should go with a stateful authentication because of the secure nature and the convenience of revoking tokens and revoking access of users and having real-time information about all the users' access. And the challenges of a stateful authentication is, of course, the limited scalability issues and the higher operational complexity with distributed systems when you have multiple servers in multiple regions and all. You have latency issues and all. So those are some of the challenges of stateful authentication in large systems. In the same way, a stateless authentication has pros. The cons of stateful authentication are the pros of stateless authentication. The pros like scalability and no session store dependency, and it's ideal for distributed architectures and mobile friendly applications where cookies are not a thing. And all those cons of stateful authentication are the pros of stateless authentication. But the cons are here is token revocation is complex, and that is one major issue, that once you issue a JWT token, until it expires, you have no way of revoking access of that user. And it could be due to various reasons, because the user's account might get compromised and the user contacted you using your support channels that the user wants to revoke that session. The user wants to stop access to their account. So you don't have any way of doing that apart from changing your secret key of the JWT, which will make all the users of your platform to log out, which is a serious inconvenience. So what can you do in this case is you can devise a hybrid approach where the main web app which runs in a browser, you can choose stateful authentication for those clients. You can have a hybrid approach where you authenticate your browsers, your web apps using a stateful nature, and the servers and the clients that use your APIs in mobile apps, where mobile apps or third-party integrations between different servers, they can adopt a stateless authentication for scalability and simplicity. So you can have a hybrid approach like this to beat the cons of both the authentication methods. And now the third type of authentication method that we can discuss is API key-based. API key-based authentication caters to a completely different set of use cases as compared to the stateful and stateless authentication. So the primary reason people came up with API key-based authentication, and before you get into that, let me explain how it works. So this is how it works. You go to a platform and you have access to the platform, and you, in the UI, what you do is you go and click on generate an API key. Okay, you can generate an API key. Then you will get an cryptographically random string, cryptographically safe random string, some string, and you can use that string to gain access to the server which caters to this UI. Okay, this server which is responsible for this UI. Now you can directly gain access to this server using this API key. This is primarily why people came up with the concept of API keys. So to give you one example, everyone is familiar with the interface of ChatGPT, right? So in ChatGPT, you can open and you can type something in the search bar and you'll get a response. That is the UI. Okay, that is the UI that we interact with. But to cater to that UI, there is somewhere in the cloud, not one server, there are a lot of servers. Those are the servers that are responsible to send the response back to the client, and the client renders that text in your UI in a very nice user-friendly way so that you can read and you get what you are looking for. That's how the typical interaction works. But OpenAI, the company that created ChatGPT, they also have feature called API keys. And why do people use that? So that people who don't want to use ChatGPT, people who have different use cases of the model, the LLM model that powers ChatGPT, it can be any model, GPT-4, GPT 3.5 and all, they want programmatic access to the server. They want to, let's say they might want to create a different UI for their use case, and they want the server's response, the ChatGPT server response in that UI. How can they do that? Or they want the server's response, the response of ChatGPT, programmatically in their server. They don't want their UI. They are building some server. They want the response of OpenAI's ChatGPT and different models in the server programmatically. Okay, not in terms of UI. They need access in terms of programs. For these kinds of use cases, to provide access to your server, not your UI, not your platform, to provide access to your server to a different set of users in a confined manner, in a permission-based manner, in a expiry-based manner, to provide that kind of access, people have come up with API keys so that I can use this key, whatever key that has been generated, with some set of permissions, some set of expiry dates. I can use this key and I can attach this key in some way, in headers, or depending on the server's implementation, I can send this key back to the ChatGPT server, whatever the server that has provided me with this key. And I can do all the operations that the server's native platform can do. I can also do using the APIs. Okay, I can get the access to the server using the API key. That's the primary use case of API keys. And people have come up with it for different advantages. First thing is they are easy to generate. You just go to the UI, you click on generate, and that's it. You get an API key, and you can use that API key to programmatically access the server. Second thing, they are ideal for machine-to-machine communication. What machine-to-machine communication means is, what we generally see or what we generally use is client to machine communication, what you can say client to server communication. Here we have a UI, we interact with our mouse, we interact with our keyboard, we interact visually with the server, right? With the UI, and the UI sends programmatic requests to the server, and the server does the business logic and sends a response back, and the user renders those information, renders those responses so that we can understand and we can again interact with it. That's how the interaction works. It's visual interaction. It's client, it's human interaction. There is another kind of interaction which is called machine-to-machine interaction. Machine-to-machine interaction. So let's say I have a server. Okay, I have a server to which I have a UI here for my platform, and this is the server for my platform, and this server wants to use the ChatGPT's capabilities. So let's say in my UI, the user types something, some string, and the user sends a request to my server and says, summarize this for me, summarize this paragraph for me. What I want to do, I want to use the existing capabilities of ChatGPT server so that I can summarize that paragraph and send it back to the user. Now, this is called a machine-to-machine communication, because my server, visual machine, there is no UI here, there is no human interaction here. Everything is done programmatically. I have written code here in whatever programming languages, and that's how the server is running. So this server uses the API key that I have generated using ChatGPT's platform interface. My server is using this API key to make a request to the ChatGPT server, and it identifies my identity. It authorizes myself, my identity, whatever plan I have, whatever quota I have remaining, whatever access I have using this API. All this information is maintained in the server side, ChatGPT server, and they can identify, they can find out that those information using the API key. Okay, and I can use this key, and I can get response from the ChatGPT server, and I can send the response back to my UI. So this is how a machine-to-machine interaction looks like. I can use my server to make requests to other servers and get that response. So it is different from like visual interaction or human interaction or UI to machine interaction. API's keys are ideal for these kinds of interactions because if you imagine in our stateful or stateless based authentication methods, we need visual triggers, we need human triggers, because there is a login form where we manually have to type it out, the username and password. You have to send this request, there is some server validation happens, and the server sends back a JWT token, and you have to save that somewhere. And all these complex interactions require some kind of human interference, and that's why they are called client to server interaction. And in the machine to machine interaction, a simple workflow is you provide the machine a secret key. It saves that in whatever environment variable or some kind of secure storage, and it sends that in all the requests to identify itself instead of doing all the username, password, token, and all those workflows. And API keys are ideal for those kinds of interactions, for programmatic interactions or machine-to-machine interactions. Now let's get into our last major type of authentication, which is Auth 2.0 or OpenID Connect, whatever it is called. Okay, why do we need this? Why did we come up with it? And everything surrounding it. Up until now, we have discussed different types of authentication, stateful and stateless and API keys and all. We have a very simple setup, right? We create an account with username and password, and every time you have to provide that, authenticate yourself, and you get a token and you get a null, and that's how the whole workflow works. And the more platforms you visit, the more sites you visit in your computer, in your system, the more credentials you create, the more credentials you have to remember, or the more credentials you have to maintain if you use a password manager. This approach became a little problematic. Why? First thing is security risks. Reusing password was very common during the initial era. Now, I hope people have become more aware of this and they use automatic password generators and password managers to maintain their passwords. But during the initial internet era, reusing passwords like 12345 or the string password was very common. And a single breach compromised a lot of accounts. The first thing with this password-based approach was security risks. Reusing the same kind of passwords in multiple platforms or multiple websites. The second thing is fatigue. all this huge number of accounts to manage was very overwhelming for a single user. And that gave rise to what we call, it's a very important concept in Auth, is called delegation. Delegation. What delegation means is, we quickly came to a class of problem. A problem, for example, one website started needing access to other websites' resources. For example, a travel app like a hotel booking or a train booking app, it needed access to Gmail, your Gmail account, to scan your flight tickets, to programmatically scan your flight tickets. That is one example of one platform, one website needing access to resource of other platform. The same way, a social media app, it can be anything, Facebook or Twitter or anything, a social media app that wants to import contacts from other platform. It can be another social media platform, or it can be your Google contacts, anything, right? It wants to import resource. One platform wants to import resource from another platform programmatically. See, now you see the pattern. This was a problem this was a use case that we started to see, which eventually gave rise to Auth. So initially what happened was, the initial solution that people came up with this issue of how one platform or one website can get access to resources of another platform. This is how users came up with the solution. What they did was, they shared passwords. They started sharing passwords, and this was disastrous. This led to so many disasters, because sharing a password meant giving full access, to everything in your account, everything in your system, and there was no way to limit permissions. And the second thing was, it was impossible to revoke access. It was impossible to revoke access without changing your password everywhere, since users used same passwords everywhere, and providing your password to one platform so that that platform can access the resource of another platform meant, if you wanted to revoke the access permanently from your side, you have to change your password. Not just in this site, you have to change your password from all sites, because now one platform has access to your password and it can do anything it wants, which is a huge security issue that came up with this solution of sharing passwords for giving platforms access to resources of another platform. Okay, that was the solution people came up with initially. Right now, we have a problem that we called delegation problem. A delegation problem, which basically means providing access of one platform to another platform, providing resources of one platform to another platform programmatically by a user. And that was the time in 2007, the birth of OAuth happened, which basically meant open authorization. And it was not just a protocol, it was a very revolutionary idea. It made so many things easier in our programming world that we have now. So historically, what happened was, a couple of engineers from companies like Google or Twitter started working on standardizing a way so that user can share access from one platform to another platform, which is the delegation problem. And what they did was, they were trying to find a way to do that without sharing passwords, which was a huge security risk. So they came up with a technique of sharing tokens to share access. The idea was, this token has specific permission. So a password has all the access to your user account, while a token has specific access to a specific part of your account. For example, if you share your Google password with me, I have access to everything. I can view your Google photos, I can see your Google Maps history, and I can look at all your contacts, and I can see your calendar. I can add to your calendar, I can remove everything, I can delete everything, I can do everything I want using that password. But let's say if you share a token, and that token only has capability to read my contacts. Okay, not delete my contacts, not add to my contacts, read my contacts. Now I have permission for a specific part of a specific platform that you access, that you have, that I can access now. I can read your Google's contacts. So that was the idea that they came up with, sharing tokens instead of passwords. So there are different components of the technique that they came up with. First was the resource owner. The second was the client. Third was resource server. And the fourth was authorization server. And first thing, who is the resource owner? The user who owns the data. So in this case, let's say it's you. You are the resource owner. Who is the client? The app that is requesting access. For example, we have a social media app. Let's say it's Facebook, and it is requesting access for your contacts from your Google account. So in this case, client is Facebook. Who is the resource server in this case? It is your Google account, which is the Google server. Who is the resource server? Who is the authorization server? This is the server who issues the token for authenticating the user. This is the token that is issued by the authorization server after authenticating the user. So this is how the typical flow of Auth 1.0 look like. So we are still talking about Auth 1.0. We are yet to reach the Auth 2.0, which came after this for a couple of reasons that we'll discuss. This is what the Auth 1.0 flow looked like. First, the client redirects the user to the authorization server, Auth server. Okay, it redirects the client to the Auth server. The client, who is the client in this case? It is Facebook. Facebook redirected you to the authorization server. Now, what happens next? The user authenticates and grants permission. You click on yes, I allow, and these are the permissions that I want to give this server, and you do that. After that is successful, in the third step, the authorization server, the server that you authenticated, that you give all the permissions to, that authorization servers sends a token to the client. Who is this client in this case? It is Facebook. It sends the token to Facebook. Now the client uses the token, whatever token it got from the authorization server, it uses the token to access the resources. What is the resource in this case? Your contacts, which is in your Google server. So that's how Facebook, a client, gets access to another platform, which is Google in this case, another platform's resource, which are contacts in this case, programmatically, without you sharing the password, with specific set of permissions. So Auth 1.0 solved this problem in a very beautiful way, which eradicated the problem of sharing the password to share access. But then the Auth 1.0 protocol evolved, and we ended up with Auth 2.0, which came around 2010 or so. Auth 1.0 was pretty revolutionary. It was pretty useful, but it had some limitations. One of it was very complex for developers to implement. The whole flow was pretty complicated for developers at that time. Second, it used cryptographic signatures. Which was very error prone. So these are the two limitations, technical limitations, that what Auth 2.0 did was, first thing, it introduced bearer tokens, which is much more simpler in the whole Auth workflow. It was more vulnerable, but it made implementations more simple. Second, it allowed developers to choose flows based on the app type. Depending on whether your app is a mobile, or it is a server-side app, or it is a device-only app, or for example, a device code app, for example, a smart TV. Depending on different use cases, depending on your device that you are using these techniques on, it provided different flows. A couple of flows that you might hear is auth code flow, authorization code flow for server-side apps. Second, implicit flow for browser-based apps, which is now discouraged due to security risks. Third, client credentials flow for machine-to-machine communication. Machine-to-machine communication, like communication between two servers without any involvement of user or browsers or any human interactions. And for this, device code flow. Device code flow is used in devices where we have limited input, where we don't have inputs like keyboards and mouse and all. For example, one of a major example is Smart TV. Smart TV authentication uses a flow called device code flow. Okay. And OAuth 2.0 came with all these features. It came with bearer token, and it came with all these different types of flows for different types of devices, depending on where you are implementing your authentication. But one thing that I missed to say here was OAuth was great for authorization, but it did not solve the issue of authentication. So if you remember, authentication is providing an identity, saying who you are, and authorization is saying what can you do, what all permissions do you have, what all capabilities do you have in the platform. And authentication is who are you in the platform, what is your identity, what is your name, what is your ID and all. And authorization is what is your permission. Okay. So OAuth solved the issue of authorization using delegation, but it did not solve the issue of authentication. So that's when in 2014 or so, people came up with OpenID Connect, or simply called OIDC, which was built on top of OAuth 2.0's security mechanisms to fill the gap of authentication in the whole authorization workflow. So this is how it works. What OIDC did on top of OAuth was OpenID Connect extended OAuth 2.0 by introducing what you call as ID token. We did not have that in OAuth 2.0. And the ID token was typically a JWT. We have already discussed JWT for reasons like this, because we will keep coming across JWT is in multiple areas of authentication and authorization. That's why we discussed about JWTs in the initial part of the video. So what OpenID Connect did was it introduced a concept called ID token in the OAuth 2.0 workflow. An ID token was nothing but a JWT which had information like user ID, when they logged in, which happened because of the field issued at, and the issuing authority, who issued the token, who was the authority, who was the platform that issued the token to this user. And all this information that was in the JWT. The JWT also had information like the user's name and the user's email and all the information that the needing party wants from the other platform. And because of OpenID Connect, now you can go to any platform, and pretty much all the platforms have this feature now. You can do sign in with Google, sign in with Facebook, sign in with Discord. And those features use OpenID Connect behind the scenes to take your identity from, let's say you do sign in with Google. So what happens is it takes your identity, your email and your Google image, your Google profile picture, your name and all, whatever the profile information it asks for, it takes your identity from Google and it stores in their database, or it just uses that to identify you, to authenticate you using Google without having its own authentication mechanisms. So that's the use of OpenID Connect. It introduced a layer of identification on top of OAuth 2.0. So this is how a typical OpenID Connect based workflow works. First thing, the client in this case. So let's say you went to a platform. You went to a platform for note taking. The client, and you click on sign in with Google. So this client, the note taking app, it redirects you to the authorization server. We discussed about authorization server just before. It redirects you to the authorization server. The user logs into the Google account. Since they did sign in with Google, they log in using the Google account from the Google's authorization server, not from the client's server. They do it from the Google's authorization server. They log in, they provide whatever permissions that was asked by the client. For example, reading the user's email or the name or the profile picture, whatever. You grant those permissions, and the authorization server sends two things: an authorization code and an ID token back to the client, to the note-taking platform. Then what the client does in the second step, it uses the code. And an ID token is optional at this stage in some workflows. And when the client uses the auth code, the authorization code in the second step, it exchanges the authorization code with the server, with the resource server for a access token on behalf of the user, and an ID token. If it did not get the ID token in the first step, it gets an ID token in the second step. And the ID token will have JWTs, and inside the JWT, it will have the user's ID, user's name, different values of the user. And the access token, using the access token, the note-taking server, the client, can do different operations on behalf of the user in the resource server. So now let's say the note-taking server asked for Google Keep's access. Okay, all the notes that you have in your Google Keep, it asks for that access during the authorization workflow. So, and you granted that access. Now, when everything is done, it uses the auth code to get this access token. Now the note-taking server can store this token, this access token, and it can get all your notes from Google server using this access token on behalf of you. Now that's the use of OpenID Connect. Now the client platform, the note-taking platform, can authenticate on behalf of you. It can pose as you. It can appear as you to the Google server, and it can ask for stuff, whatever the stuff it asked permission from you. Not any kind of stuff, only the stuff it has permission for. In this case, all the notes from your Google Keep. Okay, so that's how the whole workflow works. So you can imagine Auth 2.0 and OpenID Connect together as security guards or key makers of the digital age, of the digital modern age. They ensure that no one, not a user or a platform, gets more access than they need or than they have asked for in the first place from the user. So they only get access to those resources that they have access for, that they have permission for. And protocols like Auth 2.0 and OpenID Connect make sure that it happens, it stays like that. And together, these two revolutionary technologies have transformed the internet from a password sharing chaos into a secure modern interconnected system. And because of these two technologies, we have so many new features in so many platforms that we can integrate one system into another. We can do different types of resource sharing. We can do different types of permission sharing, and all those different things that can happen because of Auth 2.0 and OpenID Connect. Now the question is, when should you use which type of authentication? Now that we discussed the 4 major types of authentication that we use in the modern age, that you should be aware of as a backend engineer, which technique, which type of authentication that you use in which kind of situation. So this can help you decide on that. So these are some of the thumb rules. Stateful authentication using a session ID or a JWT token and a persistent storage. You use stateful authentication for typically all your web app based authentication workflows, which comprise of pretty much a large portion of our SaaS based models, right? That's a stateful authentication is ideal for that kind of scenario where user specific session data is stored on the server. Okay. Stateless authentication is ideal for APIs or scalable systems which have distributed servers all over the world and where tokens carry users info or users data. We have Auth authentications. This is ideal for third-party integrations and providing login via external providers like Google, Facebook, Discord, and all. We have API key-based authentication, which is ideal for server-to-server or machine-to-machine communication or a, let's say, single-purpose client access to APIs. So that's pretty much all the 4 kinds of authentication and a simple thumb rule to decide you on when to use what. In my experience, you will use stateful authentication and stateless authentication most of your times when you're building your APIs. Okay, and with that, we have pretty much talked about everything that you need to know as a backend engineer about authentication, that you need to understand about authentication. And now we can move on to authorization. This is not as vast as authentication, but yes, you can still get a high level idea of what it is about. As I have already mentioned, the one line explanation of authorization is authentication is basically the who, which means who the identity of the user, and authorization is the permissions of the user, what a user can do, and authentication is who the user is in the platform. Those are the two questions that can help you understand the difference between authentication and authorization. Now, moving on to authorization, what was the need of it? Why did people come up with this concept called authorization? Circling back to our earlier example, let's say we have a user that logged into our system. We have a server, and let's say it's a note-taking platform. It's a note-taking platform, and the user logged into our platform or logged into our server using the appropriate credentials. So it provided the email or password or whatever the credentials need are, and it authenticated itself into the platform. Now it can create notes, it can delete notes, it can update notes, whatever the typical functionality of a note-taking platform is. That's one part. Second part comes is you as the creator of this platform. As a creator of this platform, you need to, your platform has an ability, or let's say a delete feature, and the delete feature actually does not delete the note permanently. It stores the note in kind of a recycle bin or a trash can. So the user has the ability, they can either delete it permanently or it will get automatically deleted after 30 days. After 30 days, let's say all these nodes move into another zone. They get deleted for the user, but you don't get permanently deleted from the database. They move into another zone. Let's call this dead zone. All the nodes after 30 days, they move into this zone called dead zone. Okay. And now the requirement is you as a creator of the note-taking platform, you want to access these nodes programmatically using another UI called admin UI. So you are the administrator, you're the creator UI, or another UI called creator UI. You as an administrator of this platform or a creator of this platform want to have some permission, some capability which are not granted to all the users of this platform, which are not granted to every user. You want special permissions for this platform, and you want to create another UI for yourself. For this case, one solution for that is you can, let's say, come up with a random string, and you can send this string with each API, and using that you can say that, okay, so the server will identify that this is coming from the creator, give you the access to those capabilities which are not accessible to all the users. Now the problem with that is this has security flaws. Since you are sending this special string, this God mode string in your APIs, if someone intercepts this string, they get hold of this string, they can do a lot of disastrous thing to your platform. They can entirely clean the DB, they can mess with other users' data, they can do a lot of stuff. There is a huge security risk with this approach. That is the first part. The second part is, what if you want to give the same level of access, the same level of special access to other users, let's say to your friends, people who regularly maintain the platform. You want to give them these special permissions. So now you have to either give that string to them, or you will create more strings and add the support in your server to allow for those strings for the special permissions. Now, as you can see, the system just got more complicated than it was before, and it is very difficult to manage the access now, and it is more prone to security flaws. Use cases like these, I have oversimplified the use case, but all in all, what you can say is providing specific permissions to specific users on a platform is basically called authorization. What authorization means is, not all users in the platform have the same level of access. Not all users can do the same thing. Some users have different capabilities. Some users have more capabilities. Some users have less capabilities. Some users have completely different set of capabilities than the other users. And if you are building a multi-tenant architecture, let's say you are providing users to create organizations, and in that organization, you want users, the admin, to provide different permissions to different kinds of members. So you want to provide the admin the capability so that the admin can assign read or write permission to some users and only read permissions to some users. So because of the need of these kinds of scenarios, people came up with authorization techniques. And one of the most famous ones that we use still in the modern age, that you as a backend engineer should be familiar with, is Arback, which stands for role-based access control. Okay. And it's called role-based access control because this is how it typically works. In a typical platform, we have different roles. One can be a user role, it can be an admin role, it can be a moderator role. We have different roles, and different roles are assigned different set of permissions. Let's say a user role is only assigned read permission. An admin role is assigned read and write permission. Same way, a moderator role is only assigned read and write permission. Depending on the role, and you can create your own custom roles with its own set of permissions on different kinds of resources. Let's say on notes, users have read, write, and delete, but on a different resource, let's say accessing the dead zone nodes, that permission is only provided to admin. You can go as granular as you want using different roles and permissions. And that's all there is to it in Arback and authorization. So this is how a typical workflow works. So in a platform, a user registers or a user signs up, and the server assigns it a role. Let's say it assigns it a user role, or depending on the use case, it assigns it a admin role. And in the subsequent requests, once the user sends its token, or it could be session ID using stateful authentication, or a JWT using stateless authentication, whatever the means of authentication it is, it sends its identification. And the server can deduce what is the role of the user using that token, or it can do a database lookup and see what the assigned role of that user is, whether the role is user or the role is admin. And depending on the role of that user, that is deduced early in the request cycle, and it is passed on to the next set of middlewares. We'll talk about middlewares and how the middleware chain works in a future video. But imagine in the first entry point, the server checks your identity and checks your role, and it attaches that information so that the next set of code, the next set of logic can have access to this information, so that they can decide whether a user has access to the dead zone nodes. And the user will have access to the dead zone nodes if the role is admin, and if the user role is user. If the role is user, then the API will fail, and the server will send an error called forbidden with status 403, which means you don't have enough permission to perform this task or access this resource. That's the whole idea of Arback, role-based access control. And that's pretty much all you need to know about authorization and Arback. Since we are talking about authentication, authorization, and it's in the context of backend engineers, two things that I want people to know. These two things is sending appropriate error messages in the authentication workflow, and some info about timing attacks. So the first thing, error messages. During the course of authentication, there will be instances when you have to send messages to the client. The user logs in with a certain email, and you could not find that email in your database, and you send a very helpful message called user not found. Or let's say the email was found, but the password is incorrect. So you sent a friendly message called incorrect password. The same way, the user tried invalid credentials for a few times, and you send a message account logged due to too many failed attempts. And while these messages are helpful for legitimate users, they also provide attackers with clues. For example, if the error indicates user not found, the attacker learns that the username does not exist, and if they're trying to breach some user's account, they will move on to the next user. They will try with a different email, and they will keep moving on to the next users if they have a certain list of users that they want to breach. The same way, if you send a message called incorrect password, now the attacker knows that the username was correct, and now they only have to breach the password. So they will try a list of brute passwords using brute forcing or dictionary attacks, and their attack surface will increase because they had some kind of confirmation from you as a server. As a backend engineer, you should be aware that never send specific messages when it is about authentication, right? Never send friendly messages like these. Always keep any message related to authentication generic. So you can say authentication failed. You can do authentication failed for all the three cases. Does not matter what happens, what kind of authentication failure happens. Always send a generic message to the client so that the attacker is always confused. If it's an attacker, it's confused that what is the next set of actions they should take to breach the system. That's one important thing you have to remember. Always send generic error messages during your authentication workflows, during your authentication lifecycle. Do not send friendly, client-friendly or user-friendly error messages, particularly in this workflow. You can send user-friendly error messages during other workflows like validations or other APIs. In the security world, there is another kind of attack, even though it is rare. It is called a timing attack. And how it works is, in a typical authentication workflow, when the user submits their credential, the email and the password, first the server verifies the username or the email or the username, whatever it is provided for the first field. It verifies it. If it tries to find if it exists, if the user exists in the platform. Then the next step is, if they are handling it, they check if the account is locked or if the account is suspended for a few times because of a couple of invalid credentials that the user has tried with in the near past. So servers have this mechanism where they lock a particular user account for some time, for 2 minutes or 4 minutes or a day, if they try too many invalid authentication attempts. So the first step is find user. Second step is check if they are locked. Okay. If they are not locked. Third step is comparing the password, the provided password, with the stored hash. The stored hash that the server has stored in the database because passwords are not stored in plain text. When you sign up into a platform, your password is taken. They're hashed into a particular cryptographically safe string. Then they are stored in the database, and there is no way to get the plain text value of that password even for the server, right? The server can only encrypt that password into a particular string, and then it can store that password so that the next time you provide your password, it can hash that password, it can encrypt that password into the same form. It can fetch the previously stored password from the database, and then it can compare those two. That's the way servers check if the password is correct or not. That's the typical workflow of checking if the user has provided correct password or not. They take the provided password, they hash it using the same algorithms, using the same key, and they check that version with the stored hashed version in the database, and they check if they are same or not. If they're not same, then the password is incorrect. Okay, that is the third step, check password. And now the problem here is, if the username is invalid, in the first step, the system will terminate there only, and you will get some response that user not found. And that will have a faster response time as compared to the system failing at the third step. At the third step, where username is valid but the password is incorrect. In this case, the response will have some kind of delay because it failed in the third step, and the system will take a little longer due to the additional step of hashing the password. Hashing the password takes a little longer than doing the other operations. That's why if the username is invalid, the system will have a faster response. If the password is invalid, system will have a little delay in the response. And using that parameter, that delay, whatever 200 milliseconds or whatever the delay is, attackers can find out whether that username was correct or not, or at what step the server failed to authenticate. And they can find if the username was invalid or the password was invalid. And they can use this strategy and they can use this information to further strategize their attack plan. They can decide whether to target on the username or to target on the password based on brute force or dictionary attacks and all. So what you can do is, as a backend engineer, to defend against these kinds of timing attacks, you have to make sure that authentication systems must introduce measures to equalize the response times. One method you can use is constant time operations. There are some cryptographically secure constant time comparison functions for password hashes. These functions ensure that execution time does not vary based on the input similarity. That is one method you can use. The second method that you can use is you can simulate a response delay using whatever programming language that you're using. If you're using Node.js, you can do set timeout, or if you're using Golang, you can do time.sleep. So you can do a simulation so that even in case of username not matching, the system does not send a response immediately. It simulates some kind of response, like 200 milliseconds of delay, and then sends a response so that the attackers cannot measure the timing differences between a username failing and a password failing, because you are simulating a fake delay. But these are the two major kinds of security related information that you should have in mind while you are implementing authentication and authorization. And with that, that's all about authentication and authorization that you should know as a backend engineer. And in the next video, we'll move on to validations and transformations.